Welcome, everyone, and thank you for joining Time Series Connect, an interdisciplinary webinar series organized in partnership with the Business and Economic Statistics session of the American Statistical Association. And I'm Yao Zheng, Associate Professor of Statistics at University of Connecticut. I'm delighted to co-host today's webinar with my colleague and co-organizer, Professor Dongjin Song from UConn School of Computing. And as usual, we'll begin with a 45 minutes talk, followed by a 10 minutes Q&A to conclude the first hour. And after that, we'll host a half-hour virtual coffee session structured as a moderated interview where we'll also invite questions from the audience. And this event is being recorded. Please feel free to submit questions in the chat or raise your hand so we can unmute you. We hope to create an open and welcoming space and appreciate your participation. And now I'm pleased to invite my co-host, Professor Song, to introduce today's speaker.
Yeah, thanks, Liao. Yeah, it's our great pleasure to have Professor Jingchao Ni from University of Houston. So Professor Jingchao Ni currently is assistant professor in the Department of Computer Science. Prior to that, he was a researcher at the NEC Labs from 2018 to 2022, and he was also a researcher at the AWS AI Lab from Amazon from 2022 to 2024. Before that, he received his PhD degree from Pennsylvania State University. His research is centered around machine learning, data mining, artificial intelligence, with a focus on time series analysis through cross-modal learning, multimodal integration, and LLM reasoning. So his research has been extended to many applications in healthcare, biomedicine, cyber-physical system, and AI OOPs. And he also has published many top-tier research papers in like ICLR, ICML, NURBS, and also top-tier journals like TKDE, TKDD, and also he has filed more than 20 patents so far. So Jingchao is also a long-term collaborator. We have been colleagues for many years, and also we have been collaborating so far. So yeah, it's our privilege to have Jingchao here to share his research. And if you have any questions during the talk, welcome to communicate with Jingchao. Yeah, he's a really nice people to communicate with and very solid researcher.
Okay. Thank you.
Jingchao, you can start.
Thank you. Okay. Thank you, Dongjin, for the introduction. And it is my pleasure to talk about our recent research in this virtual session at UConn. So today's topic is cross-modal knowledge transfer in time series AI via large vision models. So time series is a representation of signal data produced by dynamic systems. Some common sources of time series include sensor readings, wearable devices, system logs, and electronic health records. Time series data are widely observed in different applications across domains, including weather and air quality monitoring, energy planning, precision agriculture, brain computer interfaces, health-related monitoring, and traffic control for smart city. So, inspired by sequence modeling in language domain, recent progress of time series AI has experienced training some transformer-based architecture to large foundation models. In the past 2 to 3 years, we have seen different time series foundation models, along with the application of LLMs to time series. And more recently, large vision models and vision language models are being applied to time series, as marked by these orange color models. So this progress this progress shows an interest in leveraging cross-modal knowledge in time series analysis, so that we can reuse existing pre-trained large models of other modalities to solve time series problems, or integrate them with time series models for improved performance. This is the general framework for cross-modal knowledge transfer for time series. First, time series needs to be transformed to a format that can be input to LLMs, LVMs, or vision language models. Then a task-specific head is trained for adapting the models to time series tasks. There are two major approaches for this data transformation layer. Embedding alignment. Embedding alignment usually requires some efforts of model crafting, designing some model-specific alignment layers with a lot of model training. And the focus of my talk will be on the first approach of using multimodal representations of time series, particularly the visual representation of time series, which is more general and cost-effective than using embedding alignment. So the rationale of using facial representation and LVMs for time series lies in the structural similarity between images and time series. So this is well explained by an example provided by this VisionTS paper. So basically, each row or each column in an image is a sequence of continuous pixel values that is analogous to univariate time series. So by large-scale image-based pre-training, LVMs may have already learned some key time series patterns like this trend, seasonality, and sudden changes from the texture of the images. So that makes it easier to adapt large vision models to time series tasks. And this may be easier than adapting an LLM to time series task, because the encoding space of LLMs is discrete tokens. There are some other advantages of using visual representation and LVMs for time series analysis, such as there are multiple imaging methods. There are multiple imaging methods for visualizing time series for encoding different patterns in time series. And multivariate time series can be well modeled by multiple channels of images. Some imaging methods can encode long time series in a compact manner, so more historical information can be used for long-term dependency modeling and long-term forecasting. So this is the outline for the rest part of my talk. So first, I will introduce some major imaging methods for visualizing time series. In our latest survey, we have identified 8 major imaging methods from the existing literature. Among these, so these methods include line plot. Line plot may be the most straightforward way to visualize a time series as a line in a 2D space. X-axis represent time step, Y-axis represent the value of a time series. And the second method, UVH, stands for univariate heatmap. So this is a heatmap visualization of a 2D matrix, and in this matrix, each column is a period of time series, and multiple periods of the time series are stacked together to form this matrix, and heatmap is applied to transform the matrix to a RGB image. MVH is a multivariate heat map. So this is a direct application of a heat map on multivariate time series matrix. Each row is a variable, and the x-axis represents time step. And next method is GAF. It means Gramming Angular Field. Gramming Angular Field. This is a squared image. X-axis, y-axis, both are time steps. So it is a encoding of some temporal patterns or pairwise time steps. The next three methods, STFT, this is short-term Fourier transform, and wavelet transform, and filter bank transform, they produce spectrograms. And these images, they encode the dynamic frequency patterns, frequency domains of time series. The last one is RP, that is a recurrence plot. Recurrence plot is also a squared image, x, y-axis, both are time steps. So it is a grayscale image encoding some recurrent patterns in time series, but it only uses binary values to encode those recurrent patterns. So this is a summary of the 8 imaging methods, and each method has its own advantage and limitation. Among these 8 methods, only MVH multivariate heat map can encode multivariate time series directly in a single image, and all other methods encode univariate time series in one image, but extending them to multivariate time series is possible by just stacking multiple channels of images. As for general guidance on how to select imaging method for different time series tasks, we did some comparative analysis using time series classification and forecasting tasks. So this figure shows the average ranking of these 8 imaging methods on multiple benchmark datasets under each task. A lower rank means method is better. For classification, GAF is the best performing method. So it kind of suggests the temporal patterns encoded by pairwise time steps is very informative for time series classification. And for forecasting, UVH is the best, is recommended because it kind of encoded a periodic assumption that is a bias often used in time series forecasting. But these 2 tasks have different difficulty levels to these imaging methods. So for classification, we can see most of the imaging methods, it can provide a reasonable performance with above 70% accuracy, except for line plot. So the poor performance of line plot is possibly because of its ineffective use of pixel values, because in a line plot only the line have some information, but most of other pixels are just a blank space. So the information in a line plot is quite sparse. So that limitation, that kind of limit the LVM's capability in recognizing the pattern in a line plot, lead to a low classification performance. In the forecasting task, the best performing method is UVH. It is much better than other methods. Other methods have a varying degree of performance for time series forecasting. And in terms of forecasting error using MSE, even 0.2 difference may indicate a significant difference. So the varying performance of these different imaging methods may indicate there are more challenges in time series forecasting than time series classification using the visual representations. So next, I will introduce some findings when using LVMs for cross-modal knowledge transfer for time series. In our recent benchmark study, we try to evaluate whether LVMs, large vision models, are truly useful for time series analysis. And we try to answer research questions like what type of LVMs, which imaging method, and what decoding mechanism fit which time series task. And for LVMs, we considered different pre-training strategies, supervised pre-training and self-supervised pre-training. For imaging method, we considered those 8 major imaging methods for time series. And for decoding, we considered linear probing and the pre-trained decoder of LVMs. And for the time series task, classification and forecasting are most representative because classification represents a high-level task that requires the model to recognize the semantic information in the data, and forecasting is a low-level task, requires a model to do inference at the numerical level to infer numbers accurately. So because we try to understand the intrinsic capability of LVM in time series analysis, so we only did minimum modification of the model architecture. And this figure shows our the architecture of the models used in our analysis. For classification, we only added a linear head to adapt LVM encoder to time series classification. And for the forecasting task, in addition to linear probing, we also use an encoder-decoder architecture of some LVMs, such as masked autoencoder, MAE, and SIM-MIM. And this use of encoder-decoder LVM for time series forecasting follows the workflow proposed by this VisionTS method. So in this method, the look-back window of input time series is firstly segmented into small pieces. Each piece is a period, and these periods are stacked to form this matrix, 2D matrix. And heatmap is applied to visualize this 2D matrix as an image. So this is a UVH image of the input time series. And then this image will be split into a number of small patches to fit the input requirement of a Vision transformer. And Vision transformer is the building block of the LVM used here called masked autoencoder, MAE. So MAE, its pre-training strategy is reconstruction-based. It masks some patches in the input image and using an encoder-decoder structure to reconstruct those masked patches during pre-training. So to utilize this reconstruction capability of MAE for time series forecasting, VisionTS added some masked patches on the right side of the input image. And this area corresponds to the forecasting horizon of the time series. So by reconstructing those masked patches and do some reverse transformation, the forecasting can be recovered from the reconstructed patches. And in this way, the model achieves forecasting using a large vision model. So this is a zero-shot forecasting performance using MAE. And by comparing with some time series foundation model, some large language models, and some time series forecasting models, the relative strong performance of VisionTS kind of suggests the visual knowledge encoded in large vision models are transferable, and useful in time series forecasting. So in our evaluation, we did a comprehensive study covering 4 different LVMs and 8 different imaging methods on 18 datasets with comparison with 26 baselines. So the key takeaways of our benchmark study is that properly fine-tuned LVMs are useful in time series analysis, and they can achieve the state-of-the-art performance in classification tasks and forecasting tasks. But the difficulty of adapting LVMs for these 2 tasks are different. So different LVMs for classification, different LVMs and different imaging methods are generally useful. But for forecasting tasks, there are some more challenges. The current best performance is limited to some specific type of LVMs and a specific imaging method. And even for the best performing LVM-based forecaster, there is a strong bias toward forecasting periods. So generally, forecasting is more challenging than classification tasks in time series analysis. There are some key insights from our findings. For example, regarding what type of LVM best fits these 2 tasks, classification and forecasting. We have some comparative results. The left part of this figure shows the comparison of 4 LVMs on 4 benchmark classification datasets, and the right part shows a comparison on 4 forecasting datasets. As for these 4 models, those red bars shows LVMs that are pre-trained in self-supervised manner, and blue bars shows supervisedly pre-trained LVMs. So for classification, actually, there is no clear pattern by comparing these 2 types of LVMs. But for forecasting, self-supervised LVMs are much better than supervised LVMs. So this is because this may imply that reconstruction-based pre-training for those self-supervised LVMs align better with time series forecasting tasks. And for supervised LVMs, their pre-training strategy is classification, so they may align better with classification tasks. We also categorize these LVMs based on their attention mechanism. So the pure bars, those pure blue and red bars, they represent LVMs using global attention, and those shaded bars represent LVMs using window attention, local window attention. So for the classification task, we can say models using global attention is better than models using window attention. This is because using window attention basically assumes translation invariance. That means a pattern in an image should be recognized regardless of its location in the image. And this assumption works well in computer vision because usually it requires to recognize some object in an image. But in time series image, the location of a pattern may represent the time step of that pattern. So if we assume we use window attention, the model may fail to recognize some time-sensitive patterns and lead to poor performance in classification. Our ablation study tested different fine-tuning strategies of the best performing LVMs for these 2 tasks. The results provide guidance on how to fine-tune LVMs for classification task and forecasting task. We tried to fine-tune different combinations of the layers in the transformer block of the LVMs, including fine-tuning all parameters, fine-tuning all but class and mask token, and fine-tuning only MLP and norm layer, and fine-tuning only norm layer, and zero shot means freeze the whole transformer block. Train from scratch means we train the model from scratch by without using pre-training parameters. That means we re-initialize the whole model using random parameters and train it from scratch. So from the results for classification, we can see ABC, they have these three cases, they have similar performance. So that means it is enough to only fine-tune the MLP and norm layers to achieve the best performance for classification. And for the forecasting task, fine-tuning all parameters may lead to some kind of overfitting. And the best performance happens when we only fine-tune the norm layer in the transformer block. And this may be explained by norm layers' direct impact on the numerical output. Also, we identify some limitations of using LVMs for time series. And one key limitation, so this is particularly for time series forecasting task. And one key limitation of current based LVM forecaster is its strong bias toward periodicity. And this is because of its period-based imaging method. In the input image, each column is a segment, represents a segment of the input time series. And the forecasting is achieved by using the input image to reconstruct this masked area. And we tested different segment lenses. That means the different lenses of these columns. And found that the best performance happens when each segment is one or multiple periods. So that means the model favors datasets with strong periodicity, which leads to bias toward forecasting periods. And we have more results about other aspects of using LVMs for time series, such as their computational cost and the computation performance trade-off, also the impact of look-back windows. And more of our analysis can be found in our preprint paper. And in the next, I will introduce our recent method for addressing this limitation of bias by integrating LVMs in a multimodal framework. So the key idea of our solution is that if LVM is good at modeling periodic patterns of time series, then we just let it to model the periodic components of the input time series. And that motivates this design of an adaptive decomposition framework called Decomposition-based Multimodal View Framework, or DMM-V framework. This model uses a visual forecaster to do the forecasting. In the meantime, we use this visual forecaster to backcast the periodic component of the input time series, then remove it from the look-back window. The remaining part will be the input to another numerical forecaster. And the outputs of this numerical forecaster and visual forecaster will be combined by a gating mechanism. So that means we're using numerical forecaster to address the remaining components that cannot be addressed by visual forecaster. The final forecasting is adaptive combination of these two forecasters. So this kind of adaptive way to combine two forecasters is flexible and trainable, so that this numerical forecaster can fit the forecasting pattern of the visual forecaster. So using a numerical forecaster to address the limitation of LVMs, we found that this model can achieve a very good performance. It can alleviate the limitation of LVMs by comparing our method with existing multimodal baseline, visual baseline, and language baselines, and some numerical baselines. The figure on the left shows a comparison between our method and the 14 SOTA baselines in terms of their average ranking using MSE metric and MAE metric. We also did some further analysis to see whether our model can work as we expected. For example, here we try to see whether the visual forecaster in our model can effectively extract those periodic components from the input time series. The top left figure shows the input lookback window, and the bottom right figure shows the backcast from the visual forecaster in our model. And we can see the model can extract some regular and periodic components from the input time series. So that shows the model can do this kind of period and trend decomposition. We also evaluated the impact of a lookback window. So in this figure, the orange line at the bottom is our model, and the results shows our model can utilize longer lookback windows better than other baselines. And this is another advantage of using a numerical forecaster to deal with the global trend, to forecast the global trend. And this global trend is useful for modeling long-term dependency, for long-term forecasting. And finally, I will introduce our recent LVM-inspired lightweight time series forecasting model. So together with the recent development of large models for time series, we also see this increasing trend of lightweight models in time series forecasting. And these models, they try to minimize the use of model parameters while maintaining a strong forecasting performance. So the motivation for this kind of development of lightweight forecasting models comes from their unique advantage, especially for resource-constrained applications, such as efficient deployment of a forecasting model for personal use, or for small business, for small institutes that may not have strong computational power, or efficient deployment on edge devices. Actually, using a large foundation model as a one-fits-all solution may be a waste of energy and may prone to over-computation for some simple tasks, and this can raise some significant concern about carbon footprint and sustainability. Especially given a specific task, using a small and specialized model may provide the same level of performance as a large model, but they can significantly reduce computational cost. Finally, the high inference latency of large models may make them unfit to some time-sensitive tasks and online inference tasks. And in this task, a small model may be more suitable. So to reduce parameter use, a lightweight model always needs to encode certain inductive biases. And existing lightweight models, they typically use a data-driven approach that hypothesize forecasting as a result of effective modeling of certain temporal patterns that are commonly observed in time series data, such as periodicity, trend, and some frequency domain patterns, some temporal correlation patterns. However, this approach is heuristic and cannot make existing lightweight models really competitive to large models that can benefit from large-scale pre-training. So in contrast to them, we propose a new model-driven perspective that ground our hypothesis on the behavior of large models. Recently, we have explored the possibility of encoding some LVM-informed biases through careful architecture design and development of constraint functions using lightweight model as a container. So based on the idea of recovering LVM's performance using lightweight models, we propose this SVTime model, a small model inspired by LVM for time series forecasting. The design of SVTime is based on 3 LVM-informed inductive biases. And the first bias is called inter-period consistency. Actually, this is the bias I introduced before from LVM forecaster. So basically, this is a periodic bias that uses past periods to forecast the future. So this inspires us to use a linear layer to combine historical periods in the input image to reconstruct future forecast. And the second bias is patch-wise variety. Instead of using a single linear layer to combine the entire periods in the lookback window, we follow the image patch structure and use a linear layer to encode each row of patches, and for forecasting a patch in the same row. So this image patch level linear layers are more flexible, and they enable variable forecasting patterns across different within period patches. The third bias is called distance attenuating local attention. So we, by analyzing the LVM's attention weights, we found for short-term forecasting, the model focuses more on the periods that is close to the end of lookback window. But for long-term forecasting, the model focuses more on the global structure in the lookback window. So to mimic this behavior, we design an annealing constraint function that can rescale the weights in our linear layers according to the distances in the lookback window and the distance in the forecasting horizon. So putting everything together, we propose this LVM inductive bias block, which is composed of only linear layers and constraint functions. But this block has a strong bias toward periodicity, so we try to mitigate this periodic bias by encapsulate this block in a backcast residual decomposition framework that is similar to the DMMV framework I introduced before. But here we only use linear layers in this whole framework. And we tested two variants of our model. SVTime uses the first 2 biases, and SVTime T stands for tiny. It uses all 3 biases. In their model complexity, the largest term is TH. T is the length of lookback window, and H is the length of forecasting horizon. So in this work, we try to build cost-effective models with large model-like performance, because we try to use lightweight models to mimic the behavior of large models in terms of time series forecasting. And in our analysis, we compare our model with 21 baselines, including SOTA lightweight models or small models in this first block of this figure. We also compare with some complex models that are mostly composed of transformer architecture and convolutional architecture, and large models that are pre-trained foundation models, including time series foundation model, LLMs, LVM, and the Vision language model. So this figure shows the size of each model, the number of model parameters. So looking at the model parameters, our model is comparable to other lightweight time series forecasters, and much less than complex model and large models. Our model only use 0.1% of parameters of VisionTS. In terms of performance, the figure in the middle compares our small models with large models. So each dot in this figure is a model, and the bubble size is proportional to the parameter size of each model. So this figure shows the performance in terms of forecasting error using MSE and the inference time. So small models, they have small inference time, and their size are much smaller than large models. So they are more located in the left side of this region. And among these small models in the red box, only our model can provide the competitive performance to those large models, large forecasting models. And the left figure is the zoom in of a small model region. By comparing it with other small models, we can see our models provide a good balance between model size and model performance. So this is the last part of my talk. Moving forward, there are some interesting future directions for using visual representations of time series. The current LVM-based time series models are mostly evaluated on benchmark datasets. So it is promising to extend this visual knowledge to time series in different domains like healthcare, geoscience, neuroscience, traffic, and agriculture. Another direction is how to utilize visual representations to improve time series understanding and reasoning by AI agent systems. This may help address LLM's weak ability in numerical inferences, which is actually critical to time series analysis. However, most vision language models, they cannot handle time series images very well due to their lack of retraining on such data. Filling this gap may pave the way toward intelligent time series engines that can support multimodal data integration, knowledge-informed decision-making, and interactive human-in-the-loop analysis. So this concludes my talk. Thank you, and now I can take any question.
Any question from our audience?
Thank you very much for the nice talk. I have several questions. So
Okay.
This is a really interesting talk. So first of all, about the multivariate heat map. So you have axis for the time and another axis for the variables.
Mm-hmm.
And So I wonder if the order of the variable will affect the performance because different from images, right? So the order of the variable typically doesn't. It's treated as in a different way in a multivariate time series setting, right? For example, if the variables are different locations and the order have different meanings. So that's my first question.
Yeah. Actually, that is a key limitation of using MVH. And MVH actually right now is not very often used in vision-based time series analysis. So the thing you mentioned is the one key limitation because how to order time series. Right now, the figure I showed is just a random order of different variables. And also putting all variables in the same image makes it difficult to learn the correlation among those variables. So that also limits the use of MVH for time series analysis, actually. So that is the limitation. That is the key limitation.
Got it. Thank you. And yeah, I have another question about data. So because like in image settings, right? So you have each image is a data point basically, and the sample size is the number of images. But in time series, so how do you train your model? So in like a statistical, like typical classical setting, we only have a single trajectory, and then we focus that single time series based on building a model for that data. And then in your setting, because you're using methods similar to images, so do you have multiple trajectories of the same, and then they have similar patterns, and then you use multiple trajectories to focus, to do the to build the model and do the forecasting, or so yeah, I wonder how you use the data.
Right now we basically transform each variable in a multivariate time series. So each variable is one univariate time series. And using the imaging method, we can transform univariate time series to a single image, RGB image. So now it becomes a data point to a vision model as an input to a vision model. So by doing this kind of transformation, every univariate time series now becomes image data point to vision model. So we just feed this image to vision model for doing fine tuning. But in this way, it is not easy to model the dependency between different variables. And most of current analyses are based on univariate time series, and it basically assumes independence of different variables. But for some domains, this may not hold. This assumption may not hold. So that is also related to some of my related recent research. And we need to modify the architecture of LVM. We cannot directly use it by adding some spatial encoder to encode the correlation among multiple images, because each image represents one variable. So if we want to effectively learn correlation in a multivariate time series and represent every variable as one image, then we need to modify the architecture of the model, add some spatial encoder to learn those spatial dependencies. But that makes the model even larger.
Yeah, that's interesting. Yeah, that's very interesting. And then another question I have is about so you mentioned the forecasting task and the classification tasks. They have a very different performance, and forecasting is a much more challenging. Could you talk a little bit more about the possible reasons behind?
Yeah. So for classification, the model can achieve good performance as long as it can identify some distinguishable patterns from the images, right? So actually, by do some visual checking of the images from different classes, actually we can clearly see those difference. For example, if two classes of time series, they have different frequency pattern. They have different recurrent pattern. Those kind of patterns can be easily visualized, and the model just need to recognize the difference from the whole picture. Once it can identify such distinguishable patterns, it can classify images correctly. But for forecasting, the task is more challenging because model need to accurately infer numbers, accurately infer what is like a sequence of numbers in the future. But some imaging method, they actually cannot preserve the original time series values. I mean, they cannot preserve the numbers. They do some transformation, like they calculate correlation of time steps, and finally the image only preserve those correlation pattern, but the raw time series values, that information is lost. So if we use those image as input to LVM vision model, then vision model does not know what is the raw input value, what is the range of the time series values in the input, then it cannot effectively infer what is the value, what is the range of value in the future. So only some of the imaging method, I think I can go back to that page. Let me see, that is this page, this page. So only these two, UVH and MVH, these two heat map representation, they preserve the original time series value in their matrices. So for this method, the model can understand what is raw time series values, or normalize the time series values, and using those values to infer what is the numbers in the future. But for other visualization, they only encode some kind of patterns in time series, and the numerical information is lost. So that makes them ineffective for time series forecasting, and that also kind of explain the challenge of using LVMs for time series forecasting.
Yeah, that
also,
makes sense.
That relates to the pre-training strategy of models. Some LVMs, their pre-training is based on is supervised. They use classification laws to pre-train the model, but classification laws does not align with forecasting. Forecasting focuses more on predicting numbers, but classification predict labels. So in our results, we found those reconstruction-based LVMs, they fit the forecasting better, because reconstruction means predicting pixel values, predicting numbers. So that aligns better with forecasting. So yeah, using those large models for forecasting has more limitations than for classification.
Yeah, that's very informative. Thank you. So I see there are audience questions, so maybe we can address them first. I do have more questions, but I see there is someone raising their hand. Yeah, I think we can. So please feel free to unmute yourself.
Yeah, thank you, Professor, for this nice, amazing talk. And my question is, am I audible?
Yes.
Hello. No.
I can. Yeah, we can hear you. Yeah.
So my question is, in this page, what we can infer from the UVH, MVH, this kind of heat map? Like, I can understand the line plot, but others I can't get. So.
Oh, okay. So for the UVH, actually, this is a visualization of a matrix. It is a visualization of a matrix. You can consider each pixel actually is a value in a matrix, right? So this is a two-dimensional matrix, and each row actually, so for UVH, it follows the method, the workflow of this VisionTS method. VisionTS method, given univariate time series, it first segment this time series into small pieces. So each piece is one segment or a period of the time series. And this period will be, so what it does is to segment this time series into small pieces based on the period of the time series. And these small segments, they are stacked in this way to form a 2D matrix. So each column is one period of the time series, and these periods, they are ordered in a temporal order from the first period to the last period. And then we have a 2D matrix, right? So all entries in this matrix are just time series values in different periods. Then we can just use a heat map visualization of this matrix to get a RGB image of the input time series. So this is for univariate heat map. And for multivariate heat map, this is easier actually. This is easier. It is just a matrix of multivariate time series. So each row is just one variable. Each row is just one variable of the multivariate time series, and each row is a sequence of numbers represent the time series of this variable. So x-axis is the time step. So we have this matrix, right? We have this multivariate time series matrix, and the heat map can be directly applied to transform it to an image. And is this more clear?
Yeah, thank you.
Okay.
Yeah, I see a few more people. So from the order I see, there's Kang Hui Ning. Would you like to unmute yourself?
Yeah. Hi, Professor. Thanks for your presentation. I got two questions regarding the model size for time series forecasting. So the first question is, do you think the scanning law is still existing for time series forecasting? And the second question is there any possibility or principles to design effective but also efficient time series forecasting model? Yeah, that's my question.
Okay, for the first question, scaling law, I am not sure about other large models like LLMs. We tested LVMs. We tested LVMs, but we so this is kind of counterintuitive. Actually, our results is kind of counterintuitive using larger scale Bayesian model. We didn't see significant improvement compared to use the base model, for example, base MAE model for time series forecasting. So that is something actually I cannot explain this kind of observation. But we didn't see clear scaling law by using, for example, large Bayesian models for time series analysis. For the second question, what is the principle to design lightweight model? Right? Is this your second question?
Yeah.
So most existing lightweight models, their design is based on their, in my understanding, is based on their observation, their intuition of the potential useful patterns in time series that can inform forecasting future, like some recurrent patterns using, then they use different ways to encode periodic pattern, or some correlation, linear correlation between past and the future, or segment level correlation. So they have quite different ways to figure out what is the potential useful mechanism for forecasting, but most of them are they didn't provide any principle, and there are underlying design, underlying thoughts that supports or theoretical support for their design. So that's why we propose a method to ground our hypothesis on large models behavior, and we even for us for our work we don't have theoretical support, and we don't have very theoretically solid principle for designing lightweight model, but it is based on our observation, our analysis of inductive biases presented in the large models, and we try to use lightweight model, linear model, to recover those behavior. So I think this is more principled than most existing methods, but I don't have a general guideline on how to design like a very efficient lightweight model and also powerful lightweight model.
Yeah, that's very informative. Thank you very much, Professor.
Thank you. Actually, this what you asked are still open questions.
Mm-hmm.
Yeah, we have very active audience today, so we will wrap up the first hour. But if anyone want to stay and for the virtual coffee session, we will definitely use the virtual coffee session time to address more questions, because I do see that there are a few questions raised by there's still some unaddressed questions from the participants. So at this point, we just take a 1 or 2 minutes break. And then after the break, we'll go back to this virtual coffee. Thank you very much.
So with these kind of new novel models, obviously the ultimate goal here is to generate some real world impact. So I was curious that these vision-based approaches you discussed, have these started to influence actual decision making, or is this mostly in a stage where it's just showing gains in predictive performance?
I'm not sure about those large vision models impacting in other applications, like in computer vision. I guess those models may have been incorporated into some product in industry, but for the use of large vision models for time series forecasting, this is a concept appeared very recently, maybe last year. So it is quite a new research problem, like how to utilize pre-trained large models of other modalities to solve time series problem. So I haven't seen such kind of models being included in any decision-making process. So I still think it is at the research stage, experimental stage, and there are still many research questions about this kind of paradigm of within cross-modal learning for time series problems. Yeah, I don't think it right now can influence decision making, especially in some critical domains like health or finance. Yeah.
Thank you. Yeah. Matthew, would you like to go next?
Yeah, thank you for the talk, Professor. So I was just wondering, I saw that you mentioned that there's definitely areas that the vision-based, like the image-based forecasting models will lack. So, sorry, I was wondering, is there ways to combine the image-based forecasting with like the numerical methods in order to make up for the areas that the image-based models will lack, or vice versa?
Sorry, can you repeat the last sentence?
Sorry. So would there be is there a way to combine like information from image-based models like the LVMs with like more numerical models to make up for like the areas in which the LVMs are lacking when it comes to forecasting?
I'm not sure whether you're asking about the method I introduced in my presentation. So that is that decomposition framework basically combines a numerical forecaster and a vision forecaster. Right? I think that is one way to combine vision model and numerical forecaster. Actually, the visual forecaster used in our experiment can be different. I mean, the numerical forecaster can be replaced by different models, transformer-based numerical forecaster or linear layer-based forecaster. There are some other ways, actually. There are some other ways, like there are existing research that augment vision language models with numerical forecaster. Because the vision language model, it can it only has text encoder and image encoder, right? So time series can be transformed to those views, and vision language model can be applied to encode time series. And there is existing method that augment vision language model with numerical encoder, like what we use actually. They can use linear layer. They use transformer encoder to encode numerical input. But they finally need is fusion layer to combine the embeddings, the representations from these three encoders, and finally transform this fused representation into the final output. Yeah. So fusing multiple representations, multiple modalities of time series actually is the active area right now. Yeah.
Thank you, Professor.
I have another question I can go ahead with. So this is more a career-based question. So as a PhD student, we're exposed to a lot of research in academia, and the approach to that can be quite different than tackling industry problems in industry. So I was curious how your experience in industry as someone who also works in academia has influenced the type of research problems you focus on now, especially in terms of what's deployable and has real-world impact versus what's more interesting academically.
Mm-hmm. Yeah. So the research in industry and in academia are actually quite different. Sometimes you may find researchers in industry, they also publish good papers, but the research style is quite different. In industry, researchers actually research teams, they closely work with product teams, and they focus more on short-term value of their research. And in academia, we can do something that has long-term impact, right? So you can do research progressively, step by step, and our research may have multiple milestones. Not every milestone can lead to a useful method, or for example, some of my research, when we try to explore a new area, we may do some survey, we may do some benchmarking evaluation to understand the current status of that area. And after we understand all those the challenges, the open problems, and then we can propose new method, right? And we can develop new method. In industry, the progress is even faster. We don't have those. We don't have much time to do those kind of exploration. We should quickly propose new method that meet customers' needs, meet production requirement. But one good thing is in industry is our research always aligned with practice, with the practical needs. So that kind of experience influenced my current research in a way that I prefer doing research that will ultimately lead to something useful in practice. I hope my final output, the final research outcome will be useful, will be used by others. So I often focus on some research programs that can generate a broad impact instead of some narrow areas. Also, when I was in industry, my research is mostly related to those signal data, time series data. So that is why I am doing time series research in academia. Time series research has broader application, both in industry and in academia, in scientific domain, in engineering. So I think it is a good research direction for me.
Thank you so much. Matthew, did you have any other questions? I think we might have time for one more.
Yeah, thank you. I was going to ask another question. It's non-technical, but so I was interested in to know, like, what, as a researcher, what has been your like biggest challenge? And I think even specifically, like, I wonder if that challenge has came from industry or academia, since you've worked in both.
So the biggest challenge maybe after I spent half of a year time on a research topic and finally find this this direction is wrong. So that will pose a significant challenge to me, but that could happen. That could happen both in my past industry experience and academic experience. I have such kind of a situation. Even for now, my student may also have such kind of a problem. So when I have such kind of problem, I always try to avoid waste of my time. So what I really my first thought when I have such kind of problem is how to refine the research direction. Like if the problem is wrong, then I can adjust the problem a little bit to another, link it to another also meaningful problem, so that the method I develop can be somehow or partially useful for solving another problem, so that I can reuse some experience to avoid the waste of time. And actually this works in my past experience. To be able to do this, I think we need to have broad knowledge to know how the relationship between different tasks, so that when I face difficulty, when I face a challenge when solving a particular problem, then we can quickly identify some related problems that may also be solved using similar technique. Yeah, so yeah, I think this is a good question. Yeah, this is a good question. Thank you.
Thank you. Yeah, thank you for the answer.
Yeah. Thank you so much for answering all these questions. It's 12:25 now, so I'll pass it over to Dr. Song.
Yeah, thanks everyone for participating this seminar, and also thanks Jingchao for providing such a wonderful talk, and which has inspired a lot of discussions here. Yeah, I think maybe that's it for today, and let's thank Jingchao again, and yeah, if you have any further questions regarding his talk, welcome to reach out to him directly. And yeah, I think, yeah.
Thank you, everyone.
Yeah, we can end our
discussion.
Thank you, everyone. Yeah.